So we've got solve these systems of equations. So we want to be able to solve a system of linear equations, and we're going to do it in at least 3 or 4 different methods. Basically the same thing, but approaching it in a different way. This is still topic 11.1. This is what we're on. Page 411 is my go. I check that in because I know that's the first thing some of you asked. But a system of equations, this is what's on your notes, is 2 or more equations with the same unknown. Solving a system of equations means finding values for each unknown that satisfy every equation in the system. We're going to look at just 2 at the moment, right? In fact, we won't go above 2 ever. So we're just going to look at solving 2 equations. So what does that mean? Well, what I did was I used one of the methods for solving these 2 equations, which is a graphical method. I won't deal with it. I'm not having it. Not just yours. This is a graphical method. Now I did this on Desmos, which using technology, so using calculators and things, you can do it on your calculator as well at some point, but we need to go through algebraic methods first. But you can see that if I plot these 2 equations, right? So equation 1, so this is a way of laying it out, so you can start adding this to your notes now. Equation 1, I'm going to call 3x minus 2y equals 0. And equation number 2 is y equals 7 minus 2x. So I've put both of those as they are into Desmos, and I took a screenshot, and I got this, right? This red line represents one of them, this blue line represents another one. Which one's which? Is it?
I think the red line is 3 equals 2.
So you think the red one is 0, okay, and you think the blue one is why? What's your reason for it? You're correct, but what's your reason for it? Okay. So where does the blue line go through? Yeah. So this goes through 7. Okay. Now you're equating that 0 to it's a bit of a there's a couple of reasons we could say that. Yes. Okay. Yeah. Positive gradient. Yeah. So this potentially could represent the gradient, the number before the x, right? We talked about that. This is the value before the x on the other one. So this is a negative gradient. This would be a positive. Yeah, that's definitely one way to look at it. The other thing is, yeah, this one crosses at 7, which is where this one crosses. Okay, so this one is number 2, and this one is 1. All right. So that's right. So, what are lines? An infinite number of points. Okay. So there is one special point of that graph. What is it? Where the lines intersect. So this point here, what do we know about that point?
That's where
What? It's the intersection of the 2 lines, but I'm asking you to think about it in a different way. If these 2 lines are not lines, they are an infinite number of points.
what's like that they should just
Yes. Okay. So that value for x and y should work in both of those. What do I mean should work?
That's why those wrong.
Yeah. So what do we think these values are? Well, I can read it quite nicely. This is x equals 2, this is y equals 3. So if I put that in, so number 1 becomes 3 times 2 minus 2 times 3. That should equal 0, does it? So 6 minus 6 does equal 0. So that's correct. I'm happy with that one. Right. So basically, we're saying, do my values for x and y give true statements? Is the question. So number 1, it did work. Number 2, let's try it. So we should be doing 3 should be found is equal to 7 minus 2 times 2. So 3 is equal to 7 minus 4. We're good there, aren't we? All right. So actually, we are all good. Now, if I move away from that point, let's say I pick this value up here, which I believe is 6 and 9, that ordered pair. What do I know about that point? In terms of working or not working or whatever.
It won't work because of the question.
Yeah, good. So if I pick 6, 9, x equals 6, y equals 9, okay? That will only work in the first one, not the other. So, 6, 9, the ordered pair, if you remember. Let's try it. In number 1 will be 3 times 6 minus 2 times 9 should equal 0. So that's 18 minus 18 is equal to, yeah, that's good. All right. But if I do it in number 2, it should be 9 equals 7 minus 2 times 6. All right. Are we going to be so happy with that one?
No.
9 equals 7 minus 12. That's wrong. Okay. So that one doesn't work. So 6, 9 does not work in both. But the 2, 3 does work in both. So when we have a graph in front of us, it's super easy to find, right? In fact, if you're on Desmos and you just draw it in, you just have to click and it tells you exactly where it is. It's no thinking needing to happen. And once we've moved on a bit, when we use your calculators, your TIN files to do this, again, having the knowledge to know that the 2 lines cross gives you the solution is all you need, then you can use your calculator to find that point. Now you might be like, oh, that's no problem, that's easy enough. Actually, you would not believe, in the assessment, I put a question like this, here's the graph, tell me what the solution is, and all you have to do is go, there it is, read it. There's more than one person that always forgets how to do that. It's like almost the most obvious thing, it's a picture in front of us, pick that point on and they forget. Right? So it's maybe not as obvious there, or it doesn't just sit there sitting. That's why we need to focus on this at the moment. Okay? So in this case, this point, the intersection, because we now know that a line is not a line, it's an infinite number of points, that point is shared by both lines, therefore the x and y value works in both equations. Does that make sense? So one way of finding that point, you already know, is to do what?
Look at the graph.
Look at the graph. Graphing, yeah? What ways have we got of graphing? Desmos, Inspire, and by hand, right? You can pick some points and find ones that work, yeah? We've done that before. We want to be able to use a couple of methods, though, that do not involve graphing. So what does your objective say we're going to use?
Solve systems of linear equations and substitution.
Yeah, so that's what we need to talk about. Okay, so you might choose to move into your maths book now. All right. So solve using substitution, and we're going to show the solution to the one we've just done using an algebraic method. So equation number one was, what was it? 3x minus 2y equals 0. And number two was, all right, so focus on what I'm doing, not the calculator. Do the calculator another lesson. So one thing you'll notice, get into the habit of labeling your equations like number one, number two. There's an important reason for that, because they need to be identified. All right. Any ideas what you think a substitution method is? What does the word substitution mean? Is it?
Oh, no.
Like,
Not in this case.
what you could use instead
Okay. Expand on it at all? Yeah, put in something into something else.
Like choose one to find the equation of x or y, and then whichever one you're trying to find, you put the other one to 0. And then
Oh, okay. Well, that's if we were going to draw it. But that's kind of substituting 0 in. Yeah, that's using substitution. Yes?
for this one, if y is 7 minus 2x, if you substitute 7 minus 2x in y,
Why am I allowed to do that?
it's y is
they'll stay the same.
Y are the same thing, right? In both of these, x and y are the same number. Therefore, if I know that y, what does the equal sign mean? Is equivalent to same value, mean the same thing, just look different, right? So that means anywhere there's a y, I can replace it with 7 minus 2x. Equally, anywhere there's a 0, I could replace it with 3x minus 2y. That doesn't help me though, because there's no 0 in this one. Now, here's the important thing, this is why they're labelled. You can't substitute one into the same thing. So, for instance, imagine a football match, right? And, you know, a player needs substitution. Do you take the same player, do you take that player off and then put them straight back on again to replace themselves? No, it doesn't work, right? So what we must do is replace something in one equation with the information from the other. So, as Matthew says, here look, y equals, so in this one I'm going to replace this y with what y equals. Now we're not always going to have this situation, but in this case we do. So I'm going to rewrite my new number 1, okay, is now 3x minus 2y, but y is now 7 minus 2x. And that now equals 0. Right. Okay? What do you do now? So 3x minus 14 plus 4x, 2 lots of 2x is 4x, and that equals 0. Then we collect like terms. 7x minus 14 is 0, as you've said. Add 14 to both sides using our, what's it called when you do that? So what are we applying? An equivalence transformation, good. We're not moving from side to side. We've said, well, if 7x minus 14 is equal to 0, then 7x must be equal to 14. And then finally, we divide by 7, and we get x equals 2. All done? Question finished?
No.
To find
Y.
y. Alright, we now need to find y. But that is the x value. Which equation do I put x equals 2 into?
Because it says that y.
Yeah, I would go with that. I'd say if I want to know y, I put it into 2. I could put this value into the other one and work out what y needs to be, but it just makes sense. If I'm trying to find y, let's use the one that says y equals. Alright? So I am going to use x equals 2 in equation number 2. So we've got y equals 7 minus 2 times 2. So we've got y equals 7 times 4. So y equals 3. How can I check my answer is correct? Put your values into where?
7 minus 2 times 2,
Yeah,
and then 3 times 2.
good. I was just waiting for you to say it to both. Why do we have to check it with both of them? It's not that it's not going to be correct. It might not be correct. So, for instance, if I use number 1, right, to find x, and then I use number 1 again to find y, which is perfectly acceptable, there is a chance if I made a mistake that it will work with number 1, but it won't work with number 2. And if you remember the start, it said x and y must work with both. So when we do a check, we should do what we did originally, was check that it works in both. But we've already done that, and we know that x was supposed to be 2, y was supposed to be 3, so all right. Any questions on that? Perfect. You are going to be doing some more yourself. So let's just check. All right. What page is it on? Round about. That's cool. Now, you should be able to do all of those 1, 2, 3. Well, we've done number 1. You should be able to do 2, 3, and 4. 2 and 3 definitely no problem. 4 you might have to think about it a little bit. 5 we might have to talk about it together. All right, but you can at least do numbers 2 and 3, and then think why did Mr. Potts say 4 and 5 might be a little bit more difficult. But I'll go with 2 and 3. All right, go for it. 4. So in this one, it's the x equals, so I can replace any x with that. So it becomes, number 2 is now 6x 25 plus 9y minus 5y. So only this time we solve for x first because we replaced the y. But this time we're going to get the y first. Because we replace the x. No difference.
Nothing.
We've got to find them both. It doesn't matter which one you do. Yeah. So what's the next step? Bracket 6 times 25. Pardon? 150 plus 54y minus 5y equals 3. That's then 150 plus 49y equals 3. Subtract the 150. You get 49y's is minus 107. Y is therefore minus 147 divided by 49. So what's that? Negative 3. Negative. How do I find x? if you want. So if y is -3, x is 25, so use the number 1, 25 plus 9 times -3. It's 25 minus 27, so x equals -2. Rightio.